Drag because I was very, very happy to learn about this and write this project a few years back. We talked about the Caesar cipher, and I briefly mentioned other ones like AES, but I haven't. This uses the BP23. This uses the perfect cipher. There is a perfect way to encrypt data, and it's been known for centuries, which is the one-time pad. This is absolutely unbreakable for a very simple reason. In a one-time pad, you have a pad full of random letters. And each letter you use to encrypt one letter of your message, and then you cross it off and you never use it again. And you never reuse any part of the pad again, so it moves every letter a random amount. And so the problem is when you try to decrypt it, even if you tried every possible random pad, you would produce every possible combination of letters, including every possible message, and you have no way to know which one is correct. This has been a perfect system, and the problem is key distribution. The way to use it is you have to somehow deliver a pad to the person receiving the message, and it has to have enough letters in it for all the data you will ever send. So you have to give them like a whole book of this stuff, and then you can only send enough messages until you used up the book, and then you have to somehow deliver another book to them. And that key distribution problem is so inconvenient, almost nobody ever uses this system. But if you used it, it would be perfect. And so the Russian army used it in World War II. The problem is they had the key distribution problem. They didn't have enough one-time pads. So what they did was when creating the random pads, they were doing it with mechanical typewriters and carbon paper, and they put in more copies of carbon paper to make more than 2 copies of the same key and distribute it to people. And the amazing thing about this system is if you use it correctly, there are 2 copies of this random key and only the sender and receiver have them, it's perfect. But if you reuse the same key again, it shatters like glass and it's trivial to crack. You don't even need a computer to crack it, which is amazing, and that's why I thought this is great. So here's a one-time pad. Here's the key string I'm going to use. It ought to be random letters, but I'm going to use readable strings, which is, by the way, not as secure as it could be, but it's easier to understand. So unbreakable, awesome, secret, secure system. Here's my message, 407. I'm going to encrypt it with that. So here's the code that does this. And let's throw that in my Python environment. Oops, that's not it. Somehow I didn't copy it. Copy, all right. There, so here's the key and here's the plain text, and they're both just strings. So now I said ciphertext is going to be the encrypted stuff, and it starts out as empty string. Now for every character in the plain text, I'm going to get the integer value of that. The ORD function will do that from a string. I could have used bytes arrays, but I wasn't used to bytes when I wrote this code. And then this is the key. Going to be a letter. So the P is a letter from the plain text, and K is a letter from the key. And so I convert them both to numbers with the ORD function. That'll convert them to the numerical field. And now I do XOR. If you're not familiar with XOR, we'll go over it eventually in the binary. But XOR is a way to combine 2 bytes to make another byte. And what you do is every place the key has a 1, you flip the bit. And every place it has a 0, you don't flip the bit. That's all. But so it's a very common way to encrypt things. So this will perform the XOR operation. That's what the caret means, the up arrow, shift 6. So now it's going to create a new number out of those 2 numbers, and then I'm going to turn that back into a character and add it to ciphertext. So here's what happens. The input is this. That is 407 written as a hex string, as we talked about it. And, well, that's what I didn't run yet. Pardon me. Here we go. All right, there we are. So here's 407 going down on the left, and here's the hexadecimal version of those. 4 is 46, O is 6F, and so on. Here's the key, U, and when you XOR 46 and 55, you get 13, and so on. 6F and 6E XOR to 1, because these numbers are almost identical, so they have almost the same pattern of 1, so most of the 1s are flipped and turned to 0s. Anyway, this is the ciphertext. And so you combine it, this is what the ciphertext looks like in hex. So it looks pretty good. That's the one-time pad system. All right, now, if you want to decrypt it, you just have to use the same key, and you start with the ciphertext in hex, you turn it back into bytes, and you do an XOR again. One thing about XOR is you XOR with a key, and then you XOR again with the same key, it undoes itself. Because wherever the 1s are, you flip the bit, And wherever the ones are, you flip the bit again, getting back to the original value. So XOR is its own decryption. So I'll put another block of code down here. All right, so I took the output of this one, 130117, and I put it here. That's the hex encrypted data. It's the same key. Now I just do the same operation, XOR byte by byte, and add the plain text, the byte created that way. And you'll get, here they are, this U plus the key XORs back to, as you can see, 407 comes back out. So that's encryption and decryption with the one-time pad. And now, if I can figure out how to get back to my instructions, all right. So now, if you first use a known key and decrypt it, so that's just using the same code you've already seen, replacing some of the data. And this is the exciting part, the crib drag. If all you have is two ciphertexts and you don't have the key, you can totally crack it, which is bloody awesome. And the way it works, I should be able to run this and show you. If I make this big and do Python 3 crib. First, let's take a look at the code. Nano crib. All right. So I start with a key here. All right. There's more. Should be more to it. All right. That's annoying.
Just a quick question.
What's that?
Just a quick question.
Yeah.
Are these lectures going to be recorded in any way?
Yes. Everything is recorded, and they go on the class page here as YouTube videos up here. So you can, after each class, I put them up there. Very important. Good. All right. So I thought I had the crib drag ready to go here, but maybe I don't. That's annoying. Maybe I'll try and fix it right now. Let's see if I can do that. Otherwise, I may put this off till next time, but I should be able to do it. Let's see. What I want to do is I want to make an interactive program so I can try things one by one. But I think I'll do it without the interaction right now, because that'd be a fun thing for you folks to figure out. So here we have this. I've got two ciphertexts encrypted with the same key, and I want to decrypt them with the same key. So let's just go here. I should be able to do it here in my environment here. Okay, so here's ciphertext. I'm going to have ciphertext 1. All right, so ciphertext 1 is this. All right, and I'm going to have another one called ciphertext 2. And that's going to be this one. All right, and now for the key, I gave you a start. Start with the word the, and then fill in with anything to make it long enough. All right, and now let's see if we can clean this up. So the plain text, I'm going to have plain text 1 and plain text 2. All right. All right. All right. And now the ciphertext 1 is the shortest. I think I'll start with just that. So for C in ciphertext 1, take a byte of the key, which is good, and decrypt it, and add that to plain text 1. And then I want to do the same thing for ciphertext 2. So I'm going to set C2 equals ciphertext 2 sub I. Because I do have a counter I, that's good, and the key, and then I need to do C sub I. This should work. Okay, just this stuff again. Want these 3 lines again, that should do it. Yep. All right. There. C2, decrypt it. And I really don't need to print out these intermediate things. I'm going to get rid of them. All right. And plain text 2 gets that added to it. Okay, and now I'm going to print plain text 1 down here. All right. There. All right, I want a carriage return here and here. Okay, plain text 1, plain text 2, and key. Let's see how this looks. Okay, this is working. Now, what I did before was I put it all in a loop so I could feed in things. But the point is, if you guess any part of any of these, either the messages or the key, if they contain a common word like the or a, you guess that word. So when I start with the down here, now if you guessed correctly, the other two things here will become readable. If you guess wrong, they will turn into unreadable garbage. So let's try guessing something other than the. Let's try TH3. If you guessed that, then the first two are readable, but the second turns into more or less unreadable junk. So that's your clue. If you guess any part of it right, so if the word the is contained anywhere, you'll find it. And so now, this is the, and I guessed that the next letter might be a space, then I might get another letter. And when you look, now I see NEVE and YOU apostrophe. So it looks like this stuff is in fact becoming readable. Now I don't know what goes here, but I can guess what goes here. NEV, the next character is probably R, and probably a space. So if I can guess these two to be R and space, and then these will become clear. And this is what's called the crib drag. First, you choose a common word and just try it everywhere until you see some part of it get readable, and then you start guessing. And you have three opportunities to guess. You can guess either the plain text or the key, and you work your way across. And that's why I said they did this before they used computers. You could do this with just a pencil and paper. Yeah?
Is that how they figure out passwords online?
Figure out your password where?
Online, like...
No, the most common way to figure out your password online is to send you a phishing message and trick you into typing it into a fake web page. That's the main way. The other way is to just have a list of passwords, all the passwords other people have used, and guess them. Those are the most common techniques.
Okay.
Well, there are other ways. Good. Any other questions? Anyway, I want to show you that. So there's various ones that you can do here for the crib drag, and it's a lot of fun. And it's real. This was real military secret. This really hurt the Russians. Their cryptography was shattered because of this flaw. Yeah.
On the other side, you have the Germans who were very meticulous about their cryptography.
Yes, with the Enigma machine.
However, the only way they got busted was when the U.S. took one of their U-boats. They found a cryptography machine.
Yeah, I've heard two stories. One is that they had a secret mission to steal one, and the other is that the famous British cryptographer actually built a computer that could try enough combinations to break in. I haven't found out which one is true. I imagine they're both true in different ways.
But the U.S.
Turing supposedly built a big computer with the technology at the time that was able to try all the combinations.
The U.S. at one point wanted to steal a U-boat just to see what would happen.
Yeah.
They did. They found a cipher machine and code book.
Right.
So secret it was, the code book was written in water-soluble paper.
Yes. Well, that's an old trick, by the way. This is something in the British Navy, back in the days of wooden ships, in the Napoleonic Wars, they had a code book which was a system of flags that meant things in military. And every British ship had to have one, and the captain of the British ships all knew the book had a lead bar in the binding, and they knew if you get taken by the enemy, you have to throw that book overboard so they don't get it. And if you don't do that, the other army will take you prisoner, and we will pay the ransom to bring you back and then hang you. It is worth more than your life and worth more than your entire crew and your ship, that book is. If that book doesn't go overboard, it's over for you. Because they had to keep it secret, just like this. If somebody gets the code book, then you've lost all your secrecy. This is a fundamental problem. And that's why we ended up with public key encryption, which is a miraculous thing. It was a secret, U.S. military secret for 20 years, and then it was reinvented on the outside in 1979, where you can finally don't have these secret private keys anymore, which is amazing. I'll probably get to it later in the course. It's amazing stuff. Anyway, let me stop this recording. I think that's probably enough demos for today.